In the previous video, we defined the definition of a derivative. In this video, we're going to evaluate that for a specific function and state the derivatives for some standard types of functions. Okay, let's start with f of x equals x squared. So the derivative is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. It's going to be the slope of the tangent line that touches the line at f of x, and it's going to be the instantaneous slope at that point, the slope of the tangent line. So we can evaluate f prime of x by substituting in this particular limit. Limit as h goes to 0 of so f of x plus h is x plus h squared minus f of x is x squared divided by h. Okay, we can work with this function inside the parentheses there. X plus h squared is x squared plus 2xh plus h squared minus x squared divided by h is equal to so the x squared minus x squared cancels. We have 2xh plus h squared over h. Every term has an h here, so h cancels with h, which cancels h squared to h. So we have the limit as h goes to 0 of 2x plus h. So as h goes to 0, h becomes 0, straightforward enough, and 2x remains 2x, so that is equal to 2x. So this means that our derivative of d dx of x squared, as we might say, is equal to 2x. So for any given point on the curve x squared, the instantaneous slope of that curve is 2x. So at x equals 0, it's 0. At x equals 1, the slope is 2. At x equals minus 1, the slope is minus 2, etc., etc. Any point in x, we can know what the instantaneous slope of the curve is by substituting in 2x. All right, but we don't want to do this for every single function. This would be tedious and more involved to calculate this limit for other kinds of functions. So we want some shortcut rules for what these derivatives are. So I got 5 standard kinds of functions over here and what the derivatives of those functions are. All right, so for a constant function, this will be a function that is just a number, so like a number a. The derivative of a constant is equal to 0, because a constant, as I said, is constant. So it doesn't change over x, it doesn't change over time, so the slope of it at any instant is just 0. For some polynomial function, or really some monomial function, I'll say, the derivative of x to the n. Over here we showed for x squared that it's equal to 2x, which is x squared times equals 2x to the 1. So in general for x to the n, this is going to be n times x to the n minus 1 for any integer value of n. Okay, so those are polynomial functions. Nice simple rule there. For e to the x, the derivative of e to the x is equal to e to the x. So that's very nice because e to the x is its own derivative. So that function is very easy to work with for lots of things. For other numbers to the x, there's a slightly different rule, but those almost never happen in physical chemistry, so I'm not going to worry about it. Even if you want to look up what the derivative of a to the x would be, you're more than welcome to do so. All right, for trigonometric functions, logarithmic functions, the derivative of the natural log of x conveniently is going to be 1 over x. So again, that's nice because that's the natural log of x is 1 over x. Pretty simple function to take care of. All right, for trigonometric functions, sine and cosine in particular, the derivative of sine of x is equal to cosine of x. So that's convenient as well. Very standard, nice, well-behaved function that we know. And returning the favor, cosine, the derivative of cosine of x, is equal to minus sine of x. Then minus sine is minus cosine is sine. So every fourth derivative, that'll repeat. All right, so these are the basic functions, basic function derivatives for the standard kinds of functions we have to deal with all the time in physical chemistry. In the next video, we'll look at special rules so that we can take the derivative of any function of any of these combinations. But these are the building blocks from which we will base the rest of the rules from which we can take the derivative of any function that we can see.